Welcome, everyone. Thank you for attending today's SEL webinar, Improving Process Reliability with Motor Bus Transfer. Before we start, I'd like to bring a few items to your attention. Today's webinar will be an hour long, including questions at the end of the presentation. This is a broadcast-only event, and all participants are muted. If you have any questions throughout the presentation, please submit them to all panelists via the Q&A tool at the bottom right-hand corner. Any questions that are not addressed during the live event will be answered by our experts personally via email. There will be a recording available on our website as soon as possible following this presentation. We are also offering PDH credits for participation in today's live event. To receive PDH credits, you must attend at least 75% of the webinar, and no partial credits will be awarded. You will receive a certificate via email following the event. Our presenters today are Monica Mergensen and Marcos Donwell. Monica is an R&D engineering manager currently serving as the head of the Protective Relay Product Management team. She earned her MBA from Washington State University, MS from Arizona State University, and bachelor's in electrical engineering from India. Monica has 15 years experience in the protective relay industry and is an active member in both the IEEE and the Society of Women Engineers. Marcos received his BSEE from Argentina and his MS in electrical engineering, his MS in mathematics, and his PhD in electrical engineering from the Virginia Polytechnic Institute and State University. He has been with Schweitzer Engineering Laboratory since 2006, where he's presently a principal engineer. He holds several patents and has authored numerous papers related to power system protection. Our panelist today is Derek Haas, a regional technical manager who will help answer questions via WebEx during the event. I will now pass the microphone to Monica.
Thank you, Nathan. Welcome to SEL webinar. Our topic today is improving process reliability with motor bus transfer. My name is Monica Mergensen. I will start this webinar with a brief introduction to motor bus transfer and talk about the system requirements. Marcos will cover the details of different methods of transfer. Let's look at why we need reliable service. If you are a factory manager, any factory, plastic, refinery, chemical, what will be your primary focus? Factory managers are responsible for the industry process. You want your process to run continuously. You have a customer commitment every day, so you do not want any unplanned shutdowns. Personnel safety is a very important aspect of your focus as well. So for all that, we need reliable service. Reliable service means continuous process, no unplanned shutdowns, and providing a safe environment for the personnel. Motor bus transfer is necessary when the loss of operation and processes results in substantial economical loss or environmental damage. A good example would be a cement processing plant. The moment the concrete stops flowing, it starts to harden. If the cement mixer stops turning, it does not take long for the mixture to solidify. And then you need to get the jackhammer to break down the concrete. This results in financial burden due to the downtime and also bringing in the additional personnel to fix the issue. Hazardous conditions can quickly arise when there is loss of power during an industrial process, putting personnel lives at risk. The most important one is also the environmental damage that could be caused due to loss of process. This can have severe consequences that can last for decades. For example, in a nuclear power plant, loss of power can result in loss of critical functions like the cooling system. The cooling system's primary function is to pump water into the reactor to regulate its temperature. If this process stops, the reactors can quickly overheat, causing meltdowns, environmental damage, and personnel lives at risk. One of the main causes of equipment damage from a power outage is electrical surges when the power is restored. For example, if you have a lumber mill operation where logs are cut and you have a power outage while a log is in the machine, you run the risk of jamming the machine. This condition, combined with the surge in power when the power is back, it can result in severe equipment damage due to thermal overload. The same thing can happen for any motor under heavy loads. If a successful transfer is achieved, the motor would never stop. Your process will never stop. Therefore, you're mitigating the risk of damaging the equipment. Any industry where continuous process is essential, we need motor bus transfer. Reliable service is key to critical facilities to provide continuous process, avoid costly unplanned shutdowns, and above all, personnel safety. If an outage occurs, the typical cost of an outage could be $50,000. Depending on the size of the system, it can also go many times higher. The slide here shows examples of industries that need motor bus transfer. But the applicable industries are certainly not limited to just these industries. Let's look at what is motor bus transfer. Motor bus transfer is the process of disconnecting a motor bus from its normal power source and safely reconnecting it to a designated alternate power source within a short period of time. All this has to happen within a short period of time, so we are allowing the critical processes to continue without damaging the equipment. A successful motor bus transfer can save company millions of dollars each time it saves the plant from unplanned shutdowns. Motor bus transfer as a process, it is essential when you realize the operation of the process itself is more valuable than the individual pieces of the process. For example, a 10,000 horsepower compressor motor might be worth $2 million, but the loss of the entire process will cost $30 million and maybe up to 30 days of downtime. To implement motor bus transfer scheme, consider that transfer success improves as the inertia and capacitance on the system increases. A successful transfer is greatly dependent on the characteristics of the load, which is the inertia of the load. There are two requirements for motor bus transfer. First one is definitely having an alternate power source where the load can be transferred to. The second one is minimal rotating inertia that supports the load while the bus is being transferred to the alternate source. There are two modes of bus transfer, sequential and simultaneous. In the sequential mode of bus transfer, a trip command is issued first. You get the confirmation from the breaker that it is open, then you issue the close command after the normal source breaker indicates it's open. This has slightly slower transfer time, but this method definitely eliminates the risk of closing into a fault. The other one is simultaneous motor bus transfer, and just like the name mentions here, the both trip and close commands are issued simultaneously. This may be preferred bus transfer when we are doing a fast transfer. It definitely carries a risk of closing into a fault. There are two types of bus transfer initiations. External initiation, this could be from an external source like an upstream relay transfer trip scheme, and it can be caused by an overcurrent element or an undervoltage element. The other one is voltage initiation from an internal undervoltage element setting. So loss of voltage could be something as simple as upstream breaker mistakenly being open. There are four methods of bus transfer: fast, in-phase, residual, and fixed time. The first three, fast, in-phase, and residual, all the three are based on variable system conditions. And the last one, fixed time, is based on a set time decay. This is possible with internal logic. So you set a timer, and then as the timer expires, you do the transfer. The first one, the fast transfer, is when the motor bus is switched onto an alternate source with no intentional delay. It is initiated at a very high speed before the motor on the bus has a chance to slow down. That's the first fast transfer mode. The next one is the in-phase transfer. In in-phase transfer, the relay looks for alternate source to be in sync with the residual voltage on the motor bus. The transfer will be initiated when both voltages are in phase, and thereby it minimizes the transient torque on the motors. The third one, residual transfer, In this one, the relay accurately measures what is the residual voltage, and it initiates the transfer when the motor bus voltage magnitude drops below the user-selected threshold. This is applicable for low inertia loads. Now, Marcos will walk us through the details of each of these transfer methods.
Okay, so there are, we are highlighting here 4 regions. The first one is the fast transfer. As the fast transfer region, that's where the voltage is very close in magnitude and in phase between 2 systems. That's where we would attempt a fast transfer. Then there is this second region where we can attempt an in-phase transfer. In this case, the voltage magnitude is not as big, so we need to make sure that we have a very good match between the phase of the 2 systems. Then we have this blue region here where the phase angle is either too big and the magnitude might not be low enough to do a residual transfer yet. And finally, when the voltage magnitude falls within this inner circle, that's where we would start a residual transfer. And so we have settings for most of these to define all of these regions. And I'll go a little bit through those during the presentation. Okay, so the first of the transfers I'm going to consider is the fast transfer. In a fast transfer, we need 2 sources that are relatively close to each other. For example, if we have 2 completely independent sources, say one is coming from our own generation and the other is coming from an independent system as the utility, then the phase angle between these 2 systems might be very, very large. It could be 180 degrees apart because the systems are separate. So in those systems, we wouldn't allow for a fast transfer. The relay will do a live check of the phase before attempting a live fast transfer. But in any case, you would only want to allow these kind of transfers when, in principle, you have the 2 systems, the 2 feeders with a close enough phase. And so in this case, if we get an external initiation, it's like a signal that we need to transfer. So the first thing that would happen is we will send an open command to the breaker connecting the bus to the feeder. And in this case, we have a sequential transfer, which is common, avoids feeding the fault. So after we send the open command, the bus will shift instantaneously from the frequency of the system to the frequency of the sleep frequency, the average sleep frequency of all the induction motors in that bus. Okay, and with that, the magnitude of the voltage is going to start to decay because we are separated from the system, and the angle is going to start separate. Once we have confirmation that the breaker open, we can send the signal to the other breaker to close, sorry. And since all that can be done quickly without having to do any heavy computations, we can have the breaker close in a few cycles, and then we get back to being at nominal voltage and at very close to the same phase that we had before. Okay, so that's for the synchroscope view. If we go and look at the time domain of the same event, here we would get the signal to start the transfer. Here we are looking at in red we have the voltage on the source we are trying to transfer to, and in blue we see the voltage on the motor bus. So here we receive the signal to start the transfer, and we immediately send the open command to the breaker that connects us to source 1. And so there is a delay there for the breaker to actually open, to send the signal to the breaker and for the breaker to actually open. When the voltages start to separate, that's where we know the breaker open, but we still need to wait for a 52A confirmation that the breaker is effectively open. And so that's when we send the initial trip, and that's when we get the confirmation that the first bus is disconnected, that's where we send the close signal to the other breaker. And again, that signal takes a while to propagate, and the breaker closes back. The feeder connects to the bus, and the system goes back to normal operation. Okay, so now we're going to go talk a little bit on the in-phase transfer. The in-phase will happen. It will typically take longer to determine that we can do an in-phase than a fast, because the fast transfer, it's just a quick phase check, which verifies that the phase now is within boundary. We understand on within 30 degrees of what it's supposed to be on the other feeder, and that the magnet is above a threshold. So those are quick checks. For the in phase, we need to take into account the breaker close to. And the reason for that is that, say, there is a fault on source one, and that will slow down all the models and will bring the voltage down. And after the bus is separated or it's isolated from the fault, then all the motor starts recovering, the residual voltage recovers a bit, and then we have to deal with larger slip frequencies between the bus and the other feeder. In these cases, we get the signal to start transfer, so we send the signal to open our breaker door to isolate the bus. There is a time delay there, and that will cause the phase to fall outside of the initial window. So by the time we can start doing the in-phase transfer, the phase difference is too big. And so we need to wait for the phase to realign with the other system. So we coast with both breakers open for a while until we determine by measuring the phase, the frequency, and the rate of change in frequency that it's an appropriate time to send the close command to the other breaker. And that may happen before. So here in point 4, we determine that if we send the close command at this point and take into account the breaker close time, then the breaker is actually going to close when we are at 0 degrees between the two systems. And that way, we issue the command before we are in the window, but then that guarantees that we're going to get a good close. And then we go back to normal operation, but now connected to the other. Okay, so this is what that would look like in the time domain. We have again the two signals. The blue one is the one from the bus, the green one is the one from the feeder we are trying to transfer to. And we also have here the voltage magnitude because we are checking for that. And so we see yellow horizontal here that the magnitude of the other feeder is healthy, and the voltage magnitude at the bus going down as time goes by, and the motors spin down. Okay, so here we see the actual breaker open, but slightly before. After that, we get the 52A confirmation, but by that time we don't want to do an in-phase fast transfer, so we start measuring the phase, the frequency, and the rate of change in frequency. And when we determine that we can go to an in-phase at this point, so we have to wait for the voltages to align again. And at this point, we determine that if we send the close command here, the breaker will actually close when the two signals are aligned again. And so that's what the relay does. And the system goes back to normal operation there. And we see that we only have a very moderate drop in the voltage. Okay, and okay, so that's where the in-phase close happens. Okay, so the last one is the residual transfer. And in this case, there was a too severe fault outside the system that brought all the voltages down too much before initiating the transfers, or you know that the motors cannot support. I mean, the inertia is too small and the voltage will decay too fast. So that is, you would just wait until the voltage falls below user-defined threshold. And so what would happen in the synchroscope domain is we'll see that the phase starts spinning and the voltage magnitude goes down until the point where it goes below the given threshold. It's important to note here that so the frequency, the slip frequency can be high, can be 35 hertz per second. And so while we are doing a transfer, we decouple from the traditional way of obtaining phasors in such a way that we get the voltage measurement is not attenuated by tracking frequency. So we have an independent algorithm to track the frequency in such a way that we can measure the magnitude as the voltage goes down and the voltage and frequency go. When we detect that threshold, that the voltage goes below the threshold, we can just issue a close, or we can start a timer and issue a close. Okay, yeah, that's how I think I went through all this. By then, that's when the breaker opened, so we're below. We are too far out, so we cannot do the transfer. We cannot do in phase, and so we wait until we're within the threshold, and then this brings us to the vast transfer consideration. So what we need to know to do the vast transfer, can do a detailed study of all the models involved and all the loads involved in the bus, or we can have a good sample of the spin down of the models. So we just disconnect the bus and we see for different load or for load conditions that we would be interested. You can see how the voltage spins down or how the voltage goes down in frequency and voltage. And with that, we can get a good idea of how the bus transfer really will operate for each case. Okay, so the 700 BT, it's built on the 700G GD plus actually, and so we inherit several of the protective features. So we can still do overcurrent, directional, and several other protective features. And so that's including loss of potential and out of step. And it also allows for all the automatic and user and manually request for a transfer. And also it has a list of a few easy to understand settings, and we're going to be going through those later in the presentation too. Okay, so there's two main configurations that we support. One is the main, and that's one relay connected. So we have 3 voltages on figure 1, 3 voltages on figure 2, and then 1 voltage on the bus. And those can be in any combination of line to neutral or Y or delta connected PTs or single. We also we support a main configuration using two 700 BTs connected in this way. So we'll have 3 voltages here, 3 voltages on the other side of the tie breaker, and 1 voltage on the bus. And then similarly for the other 700 VT. And there is no communication required between the two bus transfer relays. It's, as we often do, a simple mirror bit communication between the two to synchronize the event reports. But other than that, the only thing that both relays need to know is the state of the breakers. Yeah, that's all I need. And the voltage distribution. Okay, for each of these applications, we have default base screens that will show in the relay, and you can go directly and control open this breaker, and it will start. You can tap on the screen, open the breaker, and it will automatically do the transfer to the other feeder. So we have this one for the main. We have these two, one for each of the two relays in a main application. Yeah, so and you can download this directly from the website. They are also included in the instruction manual CD. Okay, so we have two in the default settings of the relay. We have these two buttons dedicated to enabling and disabling the transfers and to manually start the transfer. Basically, you would use this push button to enable it using the default settings, of course. And then by pressing the button above that, you go from one feeder to the other. So if the Y breaker is closed, then the relay arms itself to transfer to the X feeder. If you push the push button, then it will do the transfer. And it takes 5 seconds to arm the transfer to the other feeder, and that depends on the 52A states. And then you can keep going back and forth between the two systems. And yeah, this I think concludes this part of the presentation. We're going to continue with a few other with the settings, and yeah, that's all I have for this part of the presentation.
Thank you, Marcos. So as Marcos mentioned, we are really excited to launch this new SEL700BT. SEL700BT has all the benefits of our very successful SEL700 series relays. I will be highlighting a few benefits of 700 series platform benefits here, but definitely do visit our website to learn more about our product. SEL700BT includes a web server. So with the web server, you can access basic device information on a standard Ethernet network with the built-in web server in the product. You can interface with the relay with any standard web browser to perform any of the following functions. You can log on with your password protection, safely read relay settings, verify relay self-test status, read relay configuration. You can inspect meter reports. You can download event history, event reports, sequential event recorder, SER data, all this from your desk using the web server. You can download all this. On the slide here, the settings of the entire Modbus transfer functionality is shown on the slide in front of you. And this is to show that how simple it is to set this product, because this is all our Modbus transfer settings that you need to set to put this 700BT in the Modbus transfer application. The relay communicates using common standard industry protocols like Ethernet IP, Modbus, 61850 edition 2, the IEC 61850 edition 2 protocol. We have DNP3, we have PRP, parallel redundancy protocol, and we have SNTP, and we have this SEL standard ASCII protocols as well. So that's our SEL700BT. You can learn more about this product at our website listed here on the slide here. Thank you for joining us today. Now we have arrived at the Q&A portion of the webinar. Please type your question in the Q&A tool chat window on your screen. Thank you very much.
Thank you, Monica and Marco. So one of the questions that came in, and I believe was answered in text by Derek, but I thought was a good one to ask the larger group, is about the current transformers. Some of the products on the market are just voltage driven. What do those current inputs bring to the 700BT?
Oh, yes. What I was going to answer on that CT question is that, for example, you can set up the directional element on the relay, and for that you need the currents. But by using the directional element, you can decide to start the transfer without any other indication. You don't need an external relay to start the transfer. You can do it on your own internally. And also you can measure all the currents and do any backup protection for any devices. Thank you for the question.
All right, thank you. A lot of times switchgear may not have three-phase PTs available. Can we still use single-phase PTs for these transfer?
Yes. For the bus, we have a single PT, and for the feeders, we are that's one of the settings in the relay. You can have any combination of PT, and it doesn't have to be the same on any of the feeders. So you can have any combination of those. Single PT will do too. You just need to specify which of the, when you close the breaker, what voltage are you going to be measuring in the feeder and on the bus. So you can say, if you have BA in both, and you say on the feeder X, for example, you have BA, and on the bus, it's you're just giving the relation between the feeder and whatever you have the PT voltage, the bus voltage connected to. So you can just give it as an angle difference between the two, or just you identify it by phase if you have it. So the short answer is yes.
All right, thank you. I don't know if we mentioned it directly. When is this 700BT going to be releasing, Monica?
It is releasing this month, so in the next week.
Thank you. So we talked a lot about fast motor bus applications, which obviously it's key application, but could this be used in a automatic transfer switch solution?
Oh, can you explain a bit more about what's involved in the automatic transfer?
I've implemented myself automatic transfer in a main time main on a 480 volt switchgear before myself, just using a PLC. Could you use the 700 BT in place of that?
The difference would be on the residual voltage on the bus, depending on the loads that you have connected. Basically, if you don't have any motor load, the residual bus on the residual voltage on the bus will go to zero as soon as you disconnect it, and that will limit. You would only be able to do simultaneous transfers where at least one of the two breakers is closed. But yes, in principle, yes, that logic is
fantastic. I've got a question here. Can this be used with synchronous motors?
In principle, yes. It would be, even from the point of view of the transfer, it's an easier job for the relay, because when you disconnect a synchronous motor bus, the frequency remains at whatever it was before on the nominal basically, and then it decays from there. And not everyone who owns synchronous motors want to do a bus transfer on synchronous machines, and that is a customer decision, but it makes the transfer easier. You have to be sure that you have enough inertia and that your motors are robust. But that's the main. That's not a problem for the relay. That's a consideration that the customer has to.
All right.
Yeah, you can use it.
Their question is, how fast can this controller transfer power from one main source to another one?
So that's limited mostly by the breaker close time and the 52As. So for the fast transfer, I think it's within the cycle. And for in phase, you just need to wait for the alignment. But in those cases, it depends on the conditions. So if you have when you lose power, it's because something happened in the system. So you had a fault. So the conditions before the fault will draw the speed of the motors down and the voltage of the bus down. And so I think the important part is to make sure that you don't ever close when you're not supposed to, and where you don't know what the voltages are going to be. So because you have the time between sending a command to when the breaker actually closes. So you need to have confidence that nothing bad is going to happen during that time. For a simultaneous fast transfer, you're sending the open and close command at the same time, and so you're limited by the breakers and the 52As.
All right, thank you. So one question came up that, can this be used in a 3-breaker main time main setting, I'm assuming? Yeah, can this 700 BT be used in a 3-breaker main time main auto transfer?
So we can use one relay, one 700 BT if it's a 2-breaker system. For a 3-breaker main time main system, we need 2 of 700 BTs. Yes, we can use that. We need 2 relays.
Thank you, Monica. Another question was in regards to 2 out-of-phase sources. What happens when both sources are out of phase? Assume source 2 is 15 degrees out of phase to source 1. Will the motor bus transfer function in the 700 BT? Will it compensate?
Okay, so how do you get 15 static degrees now? So typically that will happens when you have different loads in the different feeders. You can have any angle between the 2 sources. So the other common phase difference is 30 degrees if you have an extra delta Y power transformer in one of the feeders and not in the other. So that will give you a somewhat constant 30 degrees difference between the 2 systems. Like that's a standing phase difference. And for example, if you have 30 degrees standing phase difference, it's going to be very easy to do a transfer one way I mean, a fast transfer one way, and it's not going to be possible to do a fast transfer the other way, because as soon as you start the transfer, you're already 30 degrees behind, and the angle is growing. So then, in that case, you will not have a fast transfer. The in-phase transfer works the same. It just doesn't. It doesn't have any problem with that. That's that. I mean, we tested that with delta Y transformers and all, and very different voltages, even 180 volts too. So the standing phase difference between the two systems. And if we go back to a couple of slides, okay, you see on the top right, it says 0 degrees below the time. And on the other breaker, there is also 0 degrees. And that's telling you the angle difference between one side and the other side of the breaker. Obviously, the one on the left is 0 because the breaker is closed. The one on the right, it's 0 because it just happened to be 0 because the systems are aligned. But if there was a transformer, then that would be 30 degrees, no matter what PT connection you have. So that's telling you what the angle difference is. So basically, you know that you connected right. But back to the question, the in phase will work no problem. It will wait until the system's align. I think, did that answer the question? I'm not sure, but I think if the question is, they really will take care of the standing and balance. Yes. If the angle is more than 30 degrees when it's trying to do the transfer, the fast transfer, it will not do it. And it will just give up on the fast transfer. It will go to phase. Okay. Thank you for the question.
Thank you. This is an interesting one. A medium voltage MCC contactor dropout at 50 milliseconds. Can this relay do a fast transfer and in-phase transfer within that 50 milliseconds?
Nathan, maybe we can follow up on that question later.
We'll note it.
Let me just go over that a little bit more. Sorry, so the maximum breaker close time that the relay allows, it's 200 milliseconds. So if you have a breaker close time that's longer than that, then doing a fast transfer or an in-phase transfer, it's very risky because lots of things can happen at that time. Basically, the longer the breaker close time, the more sure you have to be that there is enough inertia in the system. But yeah, those are the limits. If you have a high inertia, then you would allow for a long breaker close time. But ideally, you will want to have a fast closing breaker for this application.
Okay, thank you. What's the advantage of using the 700 VT for a main-time-main setup versus the 751 3-box solution using our app guide?
So in this one, 700 VT does the in-phase, which it's not possible for with 3-cycle frequency measurement. Also, I mean, you saw we have very few settings. It's tested. I mean, the application guide is also well tested, but when you have to write the logic, I think everyone will agree that the hard coded logic is better. Also, we track way higher rate of change of frequencies. So the 700 VT will, for bus transfer, will do up to 35 hertz per second, which we cannot measure in any other relay.
Thank you. Another question, with the 700 VT being a new product, how did SEL test and validate the fast in-phase capabilities?
Okay, so we have we have a engineering services division, and they do bus transfer applications. And so we have lots of recordings from the field that we use to design and to test the relay. We also do quite a bit of RTDS testing in R&D. Also, engineering services has they do their own modeling for bus transfer. So we tested that too. We have spin down recordings from several models, and we also have a demo unit with the models and the main timeline application with all the auxiliary contacts and 52As, and basically applied and compared to other fast transfer relays and solutions.
Thank you. So there's several questions relating to settings of this, recommended settings. What are the, but I think maybe the more general question would be, is a spin down study necessary for setting the 700 BT for fast and in-phase transfer?
You will need to know, you will need to have an idea of how fast your bus spins down. If you have very large, so you have one motor and then you have several resistive loads, then your voltage magnitude and the frequency will decay way too fast. If it's going faster than 35 hertz per second, then the relay will detect this. It's not going to try to do a transfer, but then there is no hope for a faster in-phase transfer. So obtaining a spin down characteristic, I think it's simple enough. It's just if at some point you disconnect your models, then you can see what that is. The other one is doing modeling or having some idea of, I mean, you need to have some idea of how long those models will take to spin down and for how long you will have some voltage support on the system. So there may be cases where you don't know anything about the system, and yeah, in those cases you will need to do some extra measurements to read that. Basically, you can set the relay without knowing it, but you still need to know the breaker close times.
Okay, thank you very much. We've got a previous fast motor bus transfer solution out there based on the 451. Now we're offering the 700 BT. Can you discuss how these differ?
Yeah, I can take that. So we do have a very successful application using our SEL 451 in the motor bus transfer application. The benefit of having 700 BT is it is a smaller form factor, and it comes with an inbuilt logic. So with SEL 451, we do many hours of system study, the parameter study, and then build a complex logic equation to do the motor bus transfer application. In this one, in 700 BT, we have inbuilt logic, which simplifies the customer side of using this product in that application. Because as we showed in one of our slides, how simple the settings are. You do a simple system study and then you put the settings together. You don't have to build a complex logic equation to put this product in the application. It definitely, if you are standardized on 451, you can still buy that. We still support that. It's a great product. And if you are thinking about a smaller form factor, fast to deploy, SEL 700 BT is faster to deploy, and it has built-in logic.
On that note, Monica, this is a part of the 700 series family. So does it offer the new Ethernet IP that came out?
Absolutely, yes. So it does have all the latest benefit that you get as part of the SEL 700 series. You get a large touchscreen display, you get an Ethernet IP, you get the web server, all the benefits that we work on our active 700 series successful product line. It'll all be part of the 700 BT as well.
Does the 700 BT come with ARC flash options?
Well, in our first release that we are releasing next week, we do not have the ARC flash option, but that is something we can always think about and discuss in our future roadmap. But the first release coming out this year, this month, it does not have ARC flash.
All right. I want to give a few more minutes for people to ask final questions, but we're approaching the end of our time. And I think we've answered quite a few of them, and there's going to be some clarifying emails going out as necessary for some of these. Here's one question. Would you typically try fast transfer first, if that fails or not applicable, in-phase transfer, and last residual voltage?
Yeah, that's the sequence. The relay will will run all three algorithms at the same time, but the fast transfer, if possible, would always win. It would always be the first one, assuming that the voltage is healthy. If the voltage is not healthy from the fault that initiated the transfer, then fast, it's out of the question. You could also disable them one at a time. You can disable them independently. If you, for some reason, don't want to try a fast transfer, yeah, but that's the way. There are also cases where you might not want to do a residual transfer. So one of the reasons to do a fast transfer or an in-phase transfer is that you conserve all the energy that's on the spinning machines. But if you go to a residual transfer, maybe the machines lost too much speed, and then if you reconnect that, you have a very high rush current from all the motors speeding up, getting back to speed again, and that may not be possible. So you have to choose what to do in those cases, and that's that depends on installation.
Thank you, Marcos. We have now reached the end of the Q&A portion. If your question was not answered live, you'll receive an email answered directly from the presenters. We hope you have enjoyed today's SEL webinar. To learn more about the topic, please visit our website. Again, a recording of this presentation will soon be available at our website under Events, Recorded Webinars, and an email will also be sent out with a link. We hope you join us for future SEL webinars. Have a wonderful day.